Hi guys, in our previous concept, we try to understand how to interlink between electric dipole moment and magnetic dipole moment. And with the help of that two concepts, electric dipole moment due to an electric dipole, and the same type of concepts comes in the magnetism because of a circular loop. And we opened a very big difference thing in the electricity and magnetism. The electricity having electric monopoles like individual charges plus q and minus q, but in magnetism there is no existence of magnetic monopoles. So if we take this charge or the elementary, very basic in the electricity, but when it comes to magnetism, so it's straight away magnetic monopole. There is no magnetic monopole, sorry, straight away magnetic dipole. To find magnetic dipole, so we learned across that a current carrying loop it acts like a magnetic dipole. But in the electricity, so we need to construct a dipole, a two charges which is separated by dipole length. So this we got a dipole moment P equal to 2qa is the dipole moment in the electric field. But in magnetic field, the dipole formula you can write that P equal to mu naught upon 4 pi times 2m upon x cube. So here very interlinked character, it is little m. So this small m is nothing but magnetic moment. Magnetic moment. So it's nothing but the product of current times area. So this is very important formula. Please fix back of your head or make a tattoo. So magnetic moment equal to the product of current times area. So we declared finally a current carrying loop is not only a source of a magnetic field, but it's a magnetic dipole. It's a bold statement. A current carrying loop is a magnetic dipole. So not only this, to the existence of magnetic dipole like this current carrying loop, when dig into the very elementary level. So very elementary level means at a particle levels. So the revolving electron, protons, they do have magnetic dipole moment. Means a revolving charge. As a very basic case if we take, we know that electrons or charges are revolving around the nucleus. If I draw a very basic atomic model, suppose this is right at center. If I take a nucleus of Ze, a positive, and somewhere at here electron is revolving around the nucleus. Let it in this direction, and let it be the r is the radius, and r is the radius of the orbit. Now this electron is revolving, means it is moving. It is moving in a circular orbit. Now if I take electron charge as E, and if I write the expression for current, we can write the current equal to the rate of flow of charge Q upon T. So if I take it here charge only magnitude or direction is charge and time T. Because the electron is revolving, it takes a time to complete its rotations. Suppose if I find its time period, so how can I get the time period? So we get that from velocity equal to distance upon time. So time t equal to distance upon velocity. since it's having radius, and if you assume this is the circular orbit, so the total distance we can get in terms of circumference, that equal to 2 pi r upon velocity, we get it. Now the current expression is going to change like this: E upon, that is 2 pi r upon V, which I can rewrite as EV upon 2 pi r. So this is the current expression for a revolving electron. And write it here, suppose if you multiply, since it's having area and it's having current, can we define right at here the magnetic moment? Yeah, we can define it here magnetic moment, because what we can say, magnetic moment equal to magnetic moment, in this case if we can represent a slight difference character as a mu, which equal to the product of current times area. So mu equal to current, here I got it for electron, from electron, that equal to EV upon 2 pi r times area becomes pi r square. Now this changes mu equal to, try to cut that, what are the things going, pi gets cancelled and r in r square terms. Now the above expression will be changes as EVR upon 2. So this we define as magnetic moment of an revolving electron. And the direction of magnetic moment we can use to find the right hand rule and what we discussed earlier and all. So for a fact of its revolving electron, now if revolving electron, we can take that in as a anti-clockwise direction when current is moving in the clockwise direction. Now for a small change at here, we introduce a character known as L. So I can pronounce this letter. For a moment you can just carry like this, magnetic moment, or let me open it here. So this is nothing but what we so called as orbital magnetic moment. So that L stands for orbital quantum number. So the orbital magnetic moment mu L equal to EVR upon 2. Yeah, this expression we do not know. Let me make certain changes at here. So which we come across an expression which we already know that. Suppose if we change a little change in the orbital magnetic moment mu L equal to EVR upon 2, if we multiply and divide with a mass of electron. So this expression changes to mu suffix L equal to E upon 2 me times mvr. So here mass of electron. So here mvr is nothing but angular momentum. So that we can write that L equal to mvr. Here E stands for m suffix v, that is the mass of electron. Don't get confused with my notation v to r. Now the orbital magnetic momentum mu suffix L equal to E upon 2 suffix me times L. Suppose if I write the sign of an electron, it goes to negative sign, and the magnetic moment is exactly opposite to the orbital magnetic moment. So that's the negative sign tells about it here. The negative sign tells about it here. The angular momentum of the electron is opposite in the direction of the magnetic moment. Suppose if we take for a positive charge, negative sign tells about orbital magnetic moment, orbital magnetic moment is opposite to angular moment. So this is the condition what I have written for an electron. For an electron, so take the negative sign. Other than the electron, if you take a simple charge, for not an electron, if you take neglect the negative sign, for a charge of E, so the magnetic moment mu L equal to only magnitude of charge E upon 2 suffix E times L. For a charge E, not an electron. So I am not writing that. So here, so that magnetic moment or orbital magnetic moment and angular momentum. So these two are constants because mvr or remains constant for an electron. Suppose if you take this ratio mu L suffix upon L, the ratio of magnetic moment of an revolving electron to orbital magnetic moment, which gives to a straight away, is the ratio of E upon 2me. So this ratio mu L upon by 2L having very important in the atomic theory. So this is known as a gyrometric ratio. Gyrometric ratio. So if you know the charge to its mass of electron, then we can get the ratio. So this ratio we can also calculate by the orbital magnetic moment to angular momentum of revolving electrons. This ratio is known as gyrometric ratio. So not only that, if I go ahead a little, so from the Bohr postulates, so he gives some postulates that the angular momentum of a revolving electron equal to is an integral multiple of h by 2 pi. Or these postulates we can write as strictly, I can write that MVR equal to NH by 2 pi. Yet MVR is nothing but L. So that is one of the postulates. So in the place of above expression, if I can substitute this as a condition, so the ratio of mu L, the magnetic moment, orbital magnetic moment equal to E upon 2me upon NH upon 2 pi. So mu L equal to NEH upon 4 pi m suffix E. So here let us know about the characters. H is Planck constant, is the charge of an electron, n equal to, you know the order, the natural numbers n equal to 1, 2, 3 and so on, and pi is constant m suffix E. Now what is the minimum value of the angular momentum? What is the least value of the orbital magnetic moment? The least value of orbital magnetic moment. So if n equal to 1 and charge of electron equal to 1.6 times 10 power minus 19 and Planck's constant 6.63 times 10 power negative 34 upon 4 pi 3.141 and mass of an electron 9.11 times 10 power minus 31. So if you do this calculation at here, so we got that the minimum orbital magnetic moment value equal to 9.27 times 10 power minus 24 ampere meter square. Do you know how did this got the units? The orbital magnetic moment or magnetic moment formula, M equal to the product of current times area. Current units are ampere, area units are meter square. So ampere meter square is the unit for orbital magnetic moment. So this concept tells about that the magnetic moment even exists at an elementary level. No need to go for a current carrying loop. So this is something, it leads to a different concepts. So even at atomic levels or elementary particles level, so electron or a charge which is revolving, it do have magnetic moment. So that concepts leads about to study about the magnetic materials, just like how an iron or ferrous oxide is affected to a magnetic field. So any charge in uniform circular motion, any charge, whether positive or negative, any charge in the uniform circular motion would have an associated magnetic moment. So this dipole moment is labeled to an orbital magnetic moment. So here we have two charges in the atomic level. One is positive and one is negative. Do you call this as a dipole? Yeah, obviously it is called a dipole. And it is separated by distance r. Now this dipole moment, it is labeled. So in this case we cannot call dipole moment. Even though they are having two separate charges and they are separated by distance r. So in this case we do not call as it's having, the nucleus having dipole moment, but we call it as it's having orbital magnetic moment. That we do represent with mu suffix L, orbital magnetic moment. So the suffix L tells about the intrinsic magnetic moment. Other than this intrinsic magnetic moment, orbital magnetic moment, the electron also do have the spin magnetic moment. One is spin up, one is spin down, or that's the way you represent spin up and spin down. So what is spin up and what is spin down? So this literally says the revolving of electron or the spin magnetic momentum of electron. So but we hasten to add at here the electron spinning, but electron is an elementary particle and it does not have any access to spin around, just like an earth or top. But it do possesses intrinsic magnetic moment. Electron do possess intrinsic magnetic moment. So to understand the microscopic roots of magnetism in an iron or any kind of magnetic materials, so this intrinsic spin magnetic moment, it do help us how these magnetic materials are developed and how do they affect. So finally I conclude at here. So we do find magnetic moment at an elementary level for an electron. So that we define in terms of two things. One is orbital magnetic moment, another one is spin magnetic moment. So spin magnetic moment we don't talk much about, it's much more complicated, but our boundary is permitted up to know in detail about that orbital magnetic moment. So we define orbital magnetic moment mu suffix L. So that equal to mu L equal to E upon 2 ME times L. So here L is that angular momentum, MVR. And two important things. One is the ratio of orbital magnetic moment to angular momentum of a revolving electrons, which gives a ratio, that ratio known as gyrometric ratio. And not only that, if we can include in the place of angular momentum the Bohr postulate, which is very powerful postulate that angular momentum of a revolving electrons L equal to mvr equal to nh by 2 pi. It is an integral multiple of h by 2 pi. And by substituting to find what is the least, what is the minimum magnetic moment of a revolving electron, so that we got it at here. So mu L suffix minimum equal to 9.25 times 10 power minus 24. Here the units are interesting. That is the ampere meter square, because it's a magnetic moment. So I forgot to say at here this value. So this value is known as Bohr magneton. It's having its name. We will again come across this same concept in the coming chapter. Exclusively we can study about the atomic structure. So there we can talk about this. But right now I can say this is known as Bohr magneton. So finally I can end up by concluding that so the magnetic moment do exist in a atomic level. So that magnetic moment is for a revolving electron. Not only that, the magnetic moment is also exists for a current carrying circular loop. So thus the current carrying circular loop is a magnetic dipole. Similarly, the magnetic dipole moment also we studied in the for a revolving electron. So try to read NCERT carefully, and the direction of magnetic dipole moment, which is exactly opposite to the direction of orbital magnetic moment, angular momentum of revolving electron. Just try to clear the things carefully.